So we'll start the session after maybe 3 to 4 minutes because participants are yet to join. So we'll be starting the session week 2 of the live interactive session for the NPTEL course Electrical Measurement and Electrical Instrument by Professor Avishek Chatterjee, IIT Kharagpur. And since there are no participants, I would have liked to ask if there are some doubts from the previous week or week 2 of the NPTEL course. However, since no one has yet joined, I will proceed. However, please feel free to ask me if there are any doubts. So I gave a weekly homework problem in the previous live interactive session of week 1. And the problem was this. It is on your screen, as you can see. And I will give you one moment to just go through the problem and try it yourself again. And then I will give you and tell you how to solve the problem. So just have a look at the problem. Meanwhile, we'll wait if some more participants will join. So I hope you have seen the problem, and this is the problem. Just give me one moment. So I hope my sound is audible and you can see my screen. The problem says that a PMMC instrument has the following parameters, which is the number of turns, the length of the coil, which is 2 centimeter, and diameter of the coil D is given to be 2 centimeter again, and the air gap flux density is 0.8, that is V is given, and the spring constant is 0.5 micronewton meter per degree, and the coil is wound on an aluminium former. The coil is rotating at an angular velocity, which is omega, given by 5 radian per second. Then the estimated EMF is asked to be determined, which is induced in the entire length of the copper coil, that is around both sides of the turns for both the conductors of the coil. And if the follow-up question says that if the resistance of the coil is 60 ohms, the resistance of the external circuit which is needed to be connected is 40 ohms, and then how much eddy current will be produced in the coil, excluding the current due to any external source, and how much torque will be produced by the eddy current in the coil opposing the motion by Lenz's law, as you know. And then it is asked that find the coefficient of damping, that is torque per unit angular velocity. So damping torque, as you know, is B times d theta dt. It is a velocity dependent torque with a constant B. So don't confuse it with that B, which is the flux density. It is just a constant damping coefficient, we can tell. And it is asking you to find the coefficient of damping. And then the damping coefficient due to eddy current, it is also asking for the you first determine, and then MCQ type question is given that whether the damping coefficient due to eddy current damping in the coil depends on parameters of the instrument or depends on the external circuit. You need to determine. So hope you have noted down the question. So coming to the first part of the solution, what it is asking. The first part of the solution is asking to determine the EMF induced. EMF induced in one side of the coil or one conductor also, I can say. So as you know that the conductor is having some motion and it is subjected to an magnetic field which is of strength B is 0.8 Weber per meter square and L is given as 2 but in centimeters, so we can write 2 into 10 to the power minus 2 meters, and V is the linear velocity, which is nothing but omega into R, and omega is given in the question to be 5. So 5 into R. R means 1 by 2 of the diameter, half of the diameter. It is 1. However, it is into 10 to the power minus 2. And L is, I think, 5. It is given in the question to be. Yes. So angular velocity is 5, sorry. So angular velocity is 5 and I have determined that. So what is the EMF induced? EMF induced for one conductor is BLV, as you know, and it is 0.8 multiplied by 2 into 10 to the power minus 2. This is B. This is L multiplied by V. What is V? V is 5 into 10 to the power minus 2. And what is the unit? Units will be in volts. And if you calculate, just you try and calculate, it will come out to be 800 microvolts. So this is the first part, and then let us see what it is asking in the second part. Second part, it is asking total EMF induced. So what will be total EMF induced? It will be 2 times that, because for one conductor, the coil has 2 conductors. So for one conductor, it is BLV, and for another conductor, it will be adding the another BLV. So it will be 2 times BLV, or you can write However, it is asking see total EMF induced in the coil. So you need to multiply this with number of turns. N is number of turns. And this is for one coil. One coil means two conductors. So you need to multiply 2 times one conductor, which is one coil, and then multiply it with number of turns, which will give you the total EMF induced for the coil. So it is, just check what is the number of turns. Number of turns of the coil is already given to be 250 times 2 times BLV for one conductor, which is 800. So you calculate this and you will find out. So it is microvolt, and if you calculate, you will find out to be 400 millivolts. So now let us see the next part. So next part, it is asking us to calculate eddy current. So eddy current produced, how can you calculate eddy current produced? It is the total EMF divided by resistance of the circuit, including the external resistance. So what is the external resistance? EMF is 400 millivolts. Resistance of the coil itself is given to be 60. However, the external is 440. So R coil plus R external. So what it is? 400 millivolts divided by 60 plus 40. So it is 100. And this is the eddy current. So how much is the eddy current? 4 milliampere. Sorry, 4 ampere, right? Four milliampere, sorry. Because the answer is asking in milliampere. So you write only 4. Because it is itself asking in milliamps. So 4 milliamps. So now let us find the next part, what it is asking. Next part of this problem asks you to find the torque due to eddy current in the coil. So torque due to eddy current is nothing but G square by R times d theta dt. And G is nothing but the galvanometer constant, which is BAN. If you calculate BAN, it will come out to be 0.08 Newton meter per amps. So torque due to eddy current you can calculate. So it will be G square divided R multiplied by 5 into 10 to the power minus 2. Sorry, 5, because 10 to the power minus 2 will not come, since it is already given that it is 5 radians per second. This is omega, okay? Omega in radians per second. So hope you understand why the eddy current torque is, the eddy current torque will always try to oppose. So it will try to dampen the actual torque. So it is G square by R, which is the damping coefficient, times the, due to the coil we are taking, so it is R coil plus R external, and times the omega. So you just calculate the torque, the eddy current torque you can tell due to the coil itself. So we can write it as, it is coming out as 320 micro Newton meter. Now if you want to calculate the damping due to this torque, damping due to eddy current in coil, it is simple. How much is the damping? It is nothing but TE by omega, which is nothing but this factor only. This is the damping factor or damping coefficient, you can write. Damping coefficient or factor. So how much it is? It is nothing but 0.08 square divided by 100, which is coming out as 64 micronewton meter per radian second, radian per second. Because the units will be torque, unit of torque divided by radian per second. So unit of torque is in micronewton meter and divided by radian per second. So the damping coefficient, you can tell, due to the eddy current in the coil, is coming out as 64 micronewton meter radian per second. So let us come to the next part, which is asking you to calculate the damping. So one thing you should first note, that we have calculated the damping due to eddy current in the coil, and it is depending on external circuit parameter. So not only the instrument parameter, but also the external circuit parameter, which we are connecting to the coil, like the external resistance, because net resistance plays a role in the damping due to the eddy current flowing in the coil. So the external resistance also participates in that. Therefore, the damping due to eddy current in the coil is not only a property of the instrument, but also depends on the external parameter. So please remember that. And next part of the problem, we have the EMF. They are asking the EMF, calculate the EMF that is induced in the former. The EMF induced in the former. So how to calculate the EMF induced in the former? It is nothing but B times L multiplied by D into d theta dt. So this is the velocity term. So if you plug in the values, B you you know, L you have already been given, D times d theta dt. This is the diameter of the coil, and then d theta dt. So if you calculate, or the diameter of the former also you can say, because the coil is wound over there. So because it is an aluminum former, please remember. So the former will also participate in the interaction, that is try to oppose or damp out the actual torque due to the coil. So you can, from the parameters that are already been given in the problem, you can determine the EMF induced in the former to be 1600 microvolts. Is the EMF. And eddy current in the former is the EMF divided by the resistance. So the EMF is given to be 1600 microvolt divided by resistance of the former, so 0.8. It is already given in the problem. If you see the problem, the resistance of the former is already given to be 0.8. It is already given. So what it is coming? It is coming as 2 milliampere. And the torque produced in the former, if they ask, B times A times L. Sorry, I. So we already know I, and this is the flux. This is I in former. So flux you already know how much it is, and then multiply it with the current, which is obtained as 2 milliampere, and then you get 0.64 micronewton meter. And final part is asking coefficient of damping. Coefficient of damping is nothing but in the former. So this torque divided by the velocity, angular velocity, which is coming out as 0.64 divided by 5. It is coming out as 0.128 micronewton meter per radian per second. So you see that the damping due to the former is only depending on the parameter of the instrument, not on the external circuit. So only depends on internal parameters, internal element parameters, and not on external circuit parameters. Hope you understand. So these kind of problems are important for your understanding. Now let us come to the numericals on the ammeters and voltmeters. That is voltage and current measurement and related numericals. Okay. So the first problem is on your screen. I hope the screen is visible. Let me check. I hope the slide is visible and the problem is also visible. So first read the problem and then you can solve. So the problem is on your screen. First go through the problem and then we'll solve. Okay. So first go through the problem, and if you have any doubt in meanwhile, you can ask. I see some people joining, so you can just unmute and ask your doubt if you have some doubts.
No, sir.
Yes, so today's strength is quite less. I don't know why. So just focus on the problem and then we'll discuss. Okay. Any doubts if you have, you can just ask. Okay.
Yeah, sir.
So you are given three different circuit configuration of the same circuit. That is, you have the same ammeter and same voltmeter. What you are doing, you are connecting it at different places and taking down some readings. From that, you have to make some conclusions and also find some parameters. You have to make some conclusions about the parameters Rx, Ra, and Rb for the voltmeter and ammeter shown here as in the diagram. You have three circuit configurations and you have the same ammeter and voltmeter. However, they are connected at different places. So we need to, you have made three different circuits and you have taken down the readings. So for circuit 1, as you can see, you have the same adjustable power supply and you are connecting the voltmeter across it. And thereafter you are connecting the ammeter and you have a resistance Rx. And for the first configuration, your voltmeter reading is observed to be 420 volts and the ammeter reading 4 ampere. Second, what you did, you connected the ammeter in the line first, and then after that, which is having an obviously a internal resistance of Ra. Please note, this is the internal resistance of the meter. Similarly, this is the internal resistance of this voltmeter. They are same. They are not changing. Only what you are doing, you are connecting at different places at different times. So what is the next circuit configuration? Thereafter, you are connecting the voltmeter and then in parallel you have the Rx. And similarly in circuit 3, what you are doing, you have simple the ammeter and voltmeter. So three readings are given to you, voltage and current readings of these three circuits. And you are asked to find the value of Rx, Ra, and Rv. So any idea how to do? Anyone? I want to hear from anyone. This session needs to be interactive, but we need to have some discussion. Otherwise, it will be of no use. So how to solve? Any one of you? From any one of you?
Or
any idea?
Sir, in the circuit 1, we have given the voltage V and current I.
Yes.
So we can get an equation in the form of Ra plus Rx equals to Rv. Like sir,
Ra plus Ra, R and
like
R
sir,
resistance. These are
Yes,
resistances.
sir.
Okay, RX all are resistance.
Yes, sir.
So,
मतलब, we can equate the voltage between
correct. Correct.
voltmeter and the current
Uh,
into
correct.
resistance RA plus RX.
Correct. 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 So what you are telling is that we can use these two nodes and equate the voltage across these two nodes for the two different given scenarios because they are connected in parallel. So what you are telling is, if I assume this current recorded by the ammeter to be I for the first configuration, then I times, I am writing for circuit 1, I times RA, which is the voltage drop across that particular ammeter for the first circuit configuration, plus the voltage drop across, same current will flow, whatever current is recorded by this ammeter, same current will flow through the Rx because they are in series. So same current multiplied by Rx. Net voltage, whatever you get, is same as the voltage recorded by the voltmeter because they are connected in parallel. Up to this is clear? We don't know yet RA and Rx. Both RA and Rx are unknown. However, we know I and V. Agreed? I and V both are known for circuit 1. So what is I? 4. 4 times RA plus again 4 times Rx equals 420. So can you tell me RA plus Rx? RA and Rx are not varying with the circuit configuration. They are same because they are of the same meter and same resistance which are used. So I can write RA and Rx, the combination, to be 105. Up to this, everyone is getting or not? Please tell.
Yes, sir.
So now see the next circuit, circuit 2. What is there? We have same ammeter. So let us name this current to be maybe I, but I2 I can write, right? Because this current is different. Because now we have changed the position of the meters, and obviously the effective resistances and voltage drops will vary, and current also will vary. So this is I2. What I can write, this I is splitting. So everyone knows current division rule. It is nothing but the current coming into this node and the resistance of the, if I want to find maybe the current I2 dash maybe, then what is I2 dash? I2 dash is the impedance of the or the resistance of the other branch divided by sum of the resistances. Up to this is clear, right? Because you know this current I2 and resistance of other branch divided by sum of the two. So this current you got, which is I2 dash. Now what I can write? The voltage V2, maybe this voltage I can call V2 of across this node. This V2 voltage is nothing but I2 dash times Rx, which is I2 RA RV Rx divided by RV plus Rx. So now we have another set of equations. So what is the value of I2 and V2? 273 and 3. So it is 31, 91. Okay. You can write 91. So you have another equation for circuit 2, that RV Rx by RV plus Rx is nothing but 91. So this is another equation. Everyone got it? Or I need to explain one? Okay. So now you see circuit 3. Maybe I can do on the same screen for clarity. Circuit 3, what I can write? Simple. RA and RV. So you have two resistance of the internal resistance of the meter. So what I can write?
Sir,
For some,
IA into RV
right?
equals to V.
So the current which is flowing, maybe I can write I3. And what will be recorded by the voltmeter? The voltage across, the voltage difference I can tell of these two nodes. So what is the voltage difference across these two nodes? It is nothing but
200.
I3 times, yes, I3 times, and I can write it as the drop. So I3 times RV. Voltage is given 200. Given, which is recorded by the ammeter to be 0.2. So now you get the value of RV. So what is RV? 200 by 0.2, which is nothing but 1000. So RV you are getting as 1000. That is the internal resistance of the voltmeter. Once you get RV, you can plug RV to the circuit 2 equation. And what you are getting Rx? Can anyone tell me what is Rx? You put in the value of RV to be 1000 and try to calculate Rx. Can anyone tell me? So you can simply write as 91 RV plus 91 Rx equal to 1000 Rx. And then you can find the value of Rx to be 91,000. I am writing from here. 91 times 1000, RV is 1000. And you have divided by 1000 minus 91. So what it is? Rx. The value of Rx, what you are getting? 91,000 divided by 1000 minus 91. So around 100.11. So Rx is 100.11. Okay. Ohms. Don't forget the units. So Rx value we got and RV value we got. Now I will use equation 1, which is of the first circuit configuration, which is giving us RA plus Rx is 105. So RA plus Rx is 105 and Rx is, I just calculated 100.11. So what is the value of RA? 105 minus Rx. Rx is 100.11 ohms. So what you will get? Around 4.89 ohms. This is the value of RA. So one observation you can see that for the ammeter, the internal resistance is much smaller than that of the voltmeter. Because ideally, an ideal ammeter should have zero internal resistance and an ideal volt such that it does not load the circuit, other part of the circuit, to which it is connected in series. Because ammeter is connected in series, to which you want to measure of the branch of which you want to measure the current. And voltmeter ideally should have internal resistance of infinity, so that it does not load the other part of the circuit to which it is connected in parallel, because voltmeters are connected in parallel. So it should not effectively load the circuit. That's why we say internal impedance of the voltmeter should be much higher. And you are getting that because for the ammeter you are getting 4.89 ohms to be the internal resistance. And you can see for the voltmeter what you are getting as 1000. So effectively it is much higher compared to that of the ammeter. So this is in line to the practical scenario. Okay. And hence you can find all three the parameters RA, RV and Rx. Any problem in this equation, in this problem? We'll go to the next problem. Okay. I hope it is clear to everyone. Okay.
Yes, sir.
So let us go to the next one. I hope the screen is visible. Next problem is visible or not? Okay. Just see the problem and just try it. We'll solve it. Okay. So meanwhile you try this problem, I want to ask you one simple question. For example, if you have a PMMC type or any type of ammeter or a meter which you have connected to some circuit and you want to measure some higher current, obviously some current which is much higher compared to the current carrying capability of this meter. Now obviously you want to extend the range of that meter by connecting some shunt resistance. Agreed or not? This total combination will effectively behave to be an ammeter which can carry higher amount of current. Higher amount means much higher than the current carrying capability of this meter. That's why we use shunt resistors, right? So that you can provide a path to the excess amount of current and you can scale your meter scale accordingly such that you can measure that current. Obviously you have to provide the shunt path. Now can anyone tell me, if I increase the value of this resistance, this shunt resistance, or I can write RSH. Let me write R meter as the meter resistance and RSH as the resistance of the shunt resistor. Okay. So can anyone tell me if the value of RSH increases? Maybe I increase the value of RSH. Then the net range or net current reading ability, you can tell, current measuring range, current measurement, I can tell, net range of current measurement. What happens to this? It increases or reduces? Tell me analogically. Anyone? If I increase the resistance of the shunt path, then will it allow more current or less current to flow? Yes, hello.
Sir, in this problem, current I is fixed, outside current or not? Hello.
Am I audible? Hello.
Yes, sir.
So what I'm telling you, just try to answer this simple problem. That if I increase the shunt resistance, which is connected in parallel to the ammeter, will the current carrying capability of the overall arrangement increase or decrease?
Sir, if we increase the shunt resistance, then more current will flow through the ammeter.
Correct. But the ammeter has some current carrying capability. So overall current carrying capability will be derated, right? Will be reduced. You cannot push more current to the meter because it will blow the meter, right? So effectively what
Yes,
you are
sir.
doing when you are increasing the shunt resistor, you are actually reducing the measurement range of the current, because otherwise you have to restrict yourself to a small range, because you cannot push more current or measure more current by pushing more current into the meter. Previously, if you would have made a smaller shunt resistor, then more current, which is obviously more than the meter current carrying capability, would have flown through the shunt path. But now you are not allowing that path because you are increasing the value of the shunt resistance. So you are doing what? You are reducing the range of measurement. So we can analogically tell that RSH, if we increase, then the current carrying range or the current measurement range will reduce, because your meter has some current carrying capability and you cannot exceed that. Otherwise you will not be able to measure. Okay, the meter will blow. So now you come to this question. What we have a switch kind of thing, and we are connecting the switch either to 1, to 2, or to 3. 3 positions we have. Okay, and these are your nodes where you can access this instrument. Only these 2 points you can access. Other points, other arrangement, complete arrangement is inside this box, which you cannot access. So effectively your ammeter, you have only these 2 nodes available, A and B. Correct? Now you read the problem. What is the problem is asking that you have a maybe some switch is there which you can access, and you have 3 positions, and the full scale deflection current of this meter is given to be 50 milliampere. And obviously the coil resistance which is sitting inside this meter is given to be 1000 ohms. And the 3 ranges possible are 250 milliampere, 1250 ampere, milliampere, and 6250 milliampere. These are 3 possible current measuring ranges. Now you have to identify and analytically tell by observing the positions and obviously the effective combinations that what will be the positions which can allow corresponding amount of current. Means what is the position which will allow 250 milliampere, then what is the position of the switch which will allow 1250 milliampere of measurement, and what will be the position which will allow 6250 milliampere. That is a larger range. Try to analyze from this analogy which I just told you. You need to analytically do this, not calculate. First, you need to analytically think that what arrangement can make your combination or overall arrangement measure more current. So obviously the combination that will allow more current measurement, you will make it for 6250, that is the higher current range. And then the combination which will have a lower amount of current measuring range, you will put in 1250 milliampere range. And the least combination, least current carrying ability combination, you will put to the 250 milliampere range. So try to analyze. Just think and tell. Okay. I want to hear the answer from you. So what position will you put the switch when you want to measure 6250 milliampere, which is the highest amount of current for the given 3 options?
Sir, position 1.
Okay, so if you put in position 1, then you have a small amount of resistance, maybe R1, and then you have the meter, and then you have some resistance, which is R2 plus R3. Because these 2 points are of no use in that condition when you have plugged into 1, and your overall this R2, R3 and Rm comes in series. Agreed or not? This is position 1. So effectively your R1 is only there in the shunt path. So obviously it is the least. Now if you put in 2, position 2, what is happening? You have the meter and you have R3 only in series. However, R1 plus R2 comes in the shunt path. This is points A and B. Same for this. So you see, as you moved or shifted your slider to the new position, which is position 2, the shunt resistance slightly increased, because obviously R1, R2 and R3 are greater than 0. They are real resistances. So effectively, obviously R1 and R1 plus R2 is more than R1. So your shunt path is now having slightly higher resistance. And in position 3, what will happen? What will happen in position 3? Complete meter is there, and then total resistance R1 plus R2 plus R3 comes in parallel. So your shunt path resistance is more, much more than the previous 2. So this is the least current carrying position. Least current measurement I can write position. So whom will you allocate these to? What range? 250 milliampere, right? Position 2 you can allocate to the mid range, which is 1250 milliampere. And position 1 is the position which can be allowed to carry on measurement for the higher range, for 6250 milliampere. So you agree or not? So if you see that for 6250 you have 1, position 1, you have position 2 here, and this is third position. Now calculate R1, R2, R3. How can you calculate R1, R2 and R3? You have been given the full scale deflection current and the coil resistance. So now you also know that which position, what amount of current you are allowing for the measurement. Now can you calculate R1, R2 and R3? How will you calculate? I need 3 resistances, and do I have 3 equations? Hello? Please answer. Hello?
Yes, sir.
Please do with me. So you have 3 resistances, 3 positions, and currents are known. Why currents are known?
Sir,
They have been given, right? 6250 milliampere you have in position 1. This is 1250 milliampere in position 2. And the third position is 250 milliamps. Okay.
yes, sir. Sir, by the current division rule, we can calculate the resistances.
Okay, so what you can write, you can calculate and let me know. This is one line, right? Not much difficult problem. So how you can write 3 equations of the current division rule? So you can write for the position 1, which is of the 250 milliampere, for example. What you can write? This is the meter, let's say Rn, and then you have R1 plus R2 plus R3. And what is the full scale deflection current, you know? 50, right? So what I can write? The current flowing through the meter, I meter if I write, what will it be?
Sir, R1 plus R2 plus R3 divided by R1 plus R2 plus R3 plus Rm.
Correct.
Into 250.
Multiplied by net incoming current, right? So what is this? This you know to be 50 milliampere, right? So one equation you got R1 plus R2 plus R3 divided by R1 plus R2 plus R3 plus Rn is nothing but 5. Sorry, 1 by 5, right? So this is one equation. Then next, for position 2, what you can do, you have R3, right? And then R1 plus R2. So this is position 1, sorry, position 3, and this is position 2. So what you can write here? What is the current? 1250, right? And we know that if we have to design the R1, R2 and R3 in such a manner that for 1250 it gives full scale deflection, right? So what you can write? R1 plus R2, and then you have R1 plus R2 plus R3 plus Rm, right? And it will come out to be 50 by 1250, which is nothing but 1 by 25. Agreed? Then you have for position 1, R3 and R2 are in series and R1 is like this, and you have 6250 milliampere for position 1. So you can write R1 by R1 plus R2 plus R3 plus Rm is nothing but this 50 divided by inverse, right? Divided by 6250, which is nothing but 1 by 125, right? It is 1 by 125. So solve these three and you will get, you have three equations and you have three unknowns. You have four unknowns actually. So where will the fourth equation come from? Yes. Fourth equation you don't need because Rm is given, right? 1000 ohms, right? Any problem?
No, sir.
So just put in Rm in all these equations and you can get R1, R2 and R3 values. You want to do, because in the exam also maybe these type of problems can come. So just solve this simultaneous equation. It will be one line, okay? So what you can do, you can just put in this value R1 plus R2 plus R3 plus Rm and put it in the other equation and try to solve, okay? So solve and let me know what are the values of R1, R2 and R3. What you are getting. Yes, please try. Please let me know once you have done, okay? Because these steps are important because you need to do these steps frequently for many problems. So please try. This is important, okay? So how you are solving? Any idea?
Sir, R3 equals to 200 ohm.
Okay. And what about R1 and R2?
Sir, R1 equals to 10 ohm and R2 equals to 40 ohm.
Okay. And R3 you are getting as 200, right?
Yes, sir.
So how you solved?
Sir, we can assume the first equation, that is by the multiplying the cross multiplication, that is 5R1 plus 5R2 plus 5R3 equals to R1 plus R2 plus R3 plus Rn.
Correct. Then you put in that value in the next one.
Yes, sir.
Yes, and compare. Then one term will be eliminated. Similarly, you do this same thing with 2 and 3. Then that other term will be eliminated. Then from those two equations you do the elimination and then you get one parameter. Then you plug in that parameter with the first one, then you get the second parameter, and when you have 2, then you plug in with any equation and you will get the remaining parameter. So this is the way how you do. So use two sets of equation and try to compare and make it 1. And then ultimately you have 2, and then again from that 2 you eliminate 1, and then you have 1. So try to do eliminations, okay, of variables in the most reduced number of steps. Okay. Can I proceed, or do you have any doubt?
Yes, sir. We can proceed.
So now you see we have a voltmeter, okay, with a PMMC instrument with a series resistance, as you know, to increase the internal resistance of the voltmeter, and an ideal diode in series. So maybe you can just draw the network that you have some, maybe some circuit, and then you have the 2 nodes of which you want to measure the, across which you want to measure the voltage. Maybe name them A and B, and you have our meter with a diode. So configuration is clear, right? This is an ideal diode. Don't consider any drop. So what is the property of the diode? It only allows the flow of current when it is forward biased. So current can only flow in this direction once you apply positive voltage at the anode and negative voltage at the cathode. If the reverse voltage is applied, then the diode will not allow the conduction of the current in that direction. And the drop we neglect, right? Forward voltage drop, 0.7 drop we neglect. So it is asking you that we have a series resistance and the voltmeter gives full scale deflection of 10 volt. So if it is 10 volts, like for example here, then it gives full scale deflection with DC, okay? And while measuring AC voltage, this voltmeter 40% deflection is observed. And the frequency is 60 Hertz. I can write FAC. So first question, can PMMC measure AC? Pure AC signal, sinusoidal signal, or any AC signal, or any symmetric, maybe, or asymmetric AC signal. What you actually measure with PMMC? See, measurement it can do, but what will it give you? It will give you the average value, right? Because it is linearly related to that current. The torque, whatever you get, is linearly related, as well as with the angle of deflection. So it gives you the average value of the mean position. So if the AC signal is symmetric, what I mean by symmetry is maybe this positive half and negative half are similar in nature. Then it can give you mean value, but mean value is 0. So it will not give you the strength of the signal. Maybe the strength I can tell as peak, S peak I can tell. So the signal actually you are trying to measure is the S peak. What is the peak strength of the signal or the voltage or the current? Because in this case we have the voltmeter, so maybe the voltage. But I'm not getting the actual voltage, I'm getting the mean value, which is 0. So we cannot measure the purely AC signal. So what we have done, we have connected the diode and it will block the negative part. Because whenever diode is not conducting, what will the voltage across the meter I can tell. So if you apply maybe this kind of voltages, which is a sinusoidal or some positive, having some positive half and some negative half, either symmetric or asymmetric, doesn't need to be any difficulty. But what will the diode allow to appear? So when you have the positive part, the diode gets forward biased. And once it is forward biased, the connection is established with this node. And once the connection is established with that node of point A, then the voltage appeared across the meter is same as the supply voltage or the circuit voltage. That is the voltage across those two nodes, which is the positive lobe. But once you have the negative lobe, this diode becomes open circuit because it does not allow the flow of current or establishment of the path for the negative half. So if this terminal is open, this voltmeter is not connected properly to the point A. Hence it measures 0. Agreed or not? So only it can measure the positive half. Now you have some value of the AC signal, but it can only measure the average value, not the peak value. So please remember. So PMMC only measures the average value. Agreed? Now please read what is asked in this question. So you need to estimate the amplitude of the AC voltage if it is a perfect square wave, triangular wave, or sinusoidal wave. And please note that for same AC voltage, you have 40% deflection. So how you will solve this problem? Any idea, any guess? Anyone wants to try? But for that, for determining or for solving this problem, you first need to understand how to determine the average value of a signal and RMS value of a signal. This is very important. For this problem, you need to only determine the average value, but you need to have an idea how to determine average and RMS value of periodic signals, and that too for half wave and full wave versions. So this is the half wave, right? Why half wave? Anyone?
Because here ideal diode is used.
Yes. Well, one diode is used, right? It is not a bridge kind of arrangement, not a full bridge kind of arrangement. So if you had a bridge, then you can have full wave or full bridge kind of arrangement, where both the positive and negative halves are allowed, and the negative half will also appear like another lobe, like a bridge, right? Rectified full bridge, you must have heard. So this is not the scenario in this case, but you need to determine how to calculate average and RMS values for full or half wave configurations. Because in this problem, you need to do it for square wave, triangular wave, and sinusoidal wave. So can anyone tell me, if I have a square wave like this, if I have a triangular wave like this is case 1, this case 2, this case 3. In third case, we have sinusoidal. Let us assume this time period. This is a time periodic signal, okay? This is T and this is T by 2. Similarly, this is T by 2 and T. This is T by 2 and T. Now, if you do it for half wave, how will it look? Anyone? Only the positive half will appear. Other part, it will be 0. Similarly, if you also do it for half wave, only the positive part will appear. Negative part will be 0. This will be 0. And if you do it for the sine, then this will be the scenario, right? Maybe this is x3, this is x2, or this is y3, y2, and y1. y1 dash, y2 dash, y3 dash. And for full wave, what you can write? How will it look? y1 double dash. This will be like, then again like this, right? T by 2 and t, this time axis, right? These are all a function of time. Okay. Then this one will look how? Then again one lobe. So y2 double dash of t versus t. Then again 2 lobes of sine. Okay. This t by 2, 0 and t. This t is y3 double dash of t. Now you need to determine the RMS and average value of these 6 signals. These 6 signals. Okay. 1, 2, 3, 4, 5, 6. Now what is RMS and what is average? Anyone? Simple. How can you simply graphically tell what is RMS and what is average? How to calculate actually RMS and average of any periodic signal?
Sir, average value we can calculate by calculating the area divided by total time.
Correct. So it is area under the curve for which you are trying to calculate the average value. Area under the curve of the signal, the time varying signal, over one time period, right? So that is what is the definition of RMS. For any signal you do, you calculate the area under the total curve for one time period and divide it or mean it over one time period. Then you get the average value of that signal for that particular time period. Agreed?
Yes, sir.
Now, what is the RMS value? What is the definition of the RMS value? It is same thing, only you have to take the area under the curve for the square of that signal. And after taking the mean over one time period, you have to again do a square root. So what you need to do? You first need to take a square, then you need to take the mean of that area of that square of the signal. So, and then you need to take the root. So it is just what you did for average. You calculated the area under the curve. For RMS, you need to calculate the area under the square of the curve. Same curve, but square of that. So for average, if you calculate the area under the curve for maybe y1 of t, for RMS, you will be calculating the area under the curve for y1 square of t. And then you need to take the mean, similar like average, over one time period. But then you have another step. The final step, you need to do the square root of that total value. So if I write, so RMS is nothing but area under curve square over t, and then you mean it over t, and then you do a square root. So please note this. So this is the physical graphical significance of RMS, that it is square area under the square of the curve. How much? For one time period, and then you need to mean it over one time period, that is divided by t, and then you finally need to take the square root. So first you need to do the reverse way. First you need to do the square, then you need to do the mean, then you need to take the root. But graphically, how to do? You just take the square of the curve. Graphically, you square the curve, how it will look. If it is flat, the square of that will also be flat. If it is a ramp, square of that will be parabolic. And if it's sine, then sine square, which is also a sinusoidal signal, but with twice the frequency. Hope you understand, because sine square theta, maybe you have done in 11 and 12, is nothing but cos 2 theta. So I can write the sine square, express the sine square as a signal which is having twice the frequency, but it will be shifted version of that because it will have a offset. So what will be the range? 1 minus cos 2 theta by 2. It will be between 0 and 1, right? Positive. Because it is square of sine. So the range will be between 0 and 1 with twice the frequency. Yes, so hope you understand what is RMS and what is average, how to calculate, right? So can anyone draw the graph of this? 1 minus cos 2 theta by 2? Or the graph of sine square theta, how will it look? How will it look? Hello?
Yes, sir. Sir,
So it will be nothing
we
but
can.
cos 2 theta and then minus of that and then shifted by 1. So what is cos 2 theta? How will it look? It will look like this. And minus of cos 2 theta will look like deflection. And then you need to provide a positive shift. It will look like this. But the frequency, remember, will be twice. So you need to calculate the average value of these three, for example. So how you can do? What is the average value of the first one? Area under the graph. Maybe you assume this is A. Then A into T by 2 is the area divided by minute over the full time period. So what is the average value? Y1 bar
A by 2.
for the halfway. Then what is Y2 bar? Half into base into height. Area of the triangle. I told you area under the curve. Total area, because this part will not have any contribution. So total area becomes this only. But you need to mean it over the complete time period, which is T. So what is the area for the
A by
halfway?
4.
Correct. However, if you would have another similar lobe, then 2 times area you would have been contributed. So for the full
Yes,
wave,
sir. We
this
just
would
have
have,
to multiply by 2.
yes, correct. So Y2 double dash bar would have been A by 2 for this one. And for this one, you have Y2 bar, which is A by 4. And for this one, obviously, no need to explain, because you already, by seeing this waveform, you know this is a flat curve of strength A. So average is also A. And one more thing, How to calculate the area under the curve for one lobe of sine? Can anyone tell me?
Sir, by integration, we can calculate the area under the curve.
So what is that? 0 to pi sine theta
dt.
d theta. But you can write here
Okay.
as t, sine t dt. Omega you consider as 1. And you calculate over how much? T by 2 and mean it over 1 by t. So what is this is minus cos of t by t, and you need to do it for minus. If I remove, we'll get the reverse, t by 2 and 0. So I will go to the new page because this page is becoming. So I will add one slide, okay. Hope the new slide is visible, right? So what we are doing, we were doing just sine theta d theta, and maybe for simple you take 0 to pi and 1 by 2 pi. So what will you get? Minus cos theta by 2 pi, 0 to pi. So we get cos of 0 minus cos of pi by 2 pi, and this will be 1 minus minus 1 divided by 2 pi. It will be 1 by pi, right? So if you have v sine theta, you would have got v peak, I can tell. V peak by pi. So always remember that average of 1/2 of a sine lobe, that is nothing but the area under the curve over the whole time period, is nothing but v peak by pi. Now if you have two sine lobes, this is the half wave, and if you would have two sine lobes, then twice the area it would have contributed, and so twice the area means twice the strength. So these expressions are similar to the half wave and full wave rectified version of sine, which is nothing but the average strength of the signal. And this strength will be measured by the PMMC because PMMC measures average. If we assume to be sinusoidal, right? Agreed?
Yes, sir.
So for half wave it is V peak by pi, and for full wave it is 2 times V peak by pi. Now let's find the RMS for the same signals. Can you help me with the RMS? What is RMS for square? For the half? What is the area under the square of the curve? A square, because I squared the signal, times t by 2, mean over t, whole root over. What is it? A by root 2. So RMS is A by root 2. However, for the full strength, full wave, RMS is A. First part done. Then next part. What is the RMS under, what is the area under square of the signal if it is triangular? Any idea? Yes, please.
No, sir.
These things are important. Okay, so you need to understand, and if you have any doubt, you please tell me. So see, this is the 0 to t by 2, and this is t. So what will this signal look like if I square it? Maybe a new page I can write. Say for example, this is the signal. So what will be y square of t? How will it look? How will it look? Parabolic, like. Sorry, this part will not come because it is not full wave. But the analysis for half wave, if you understand, yes, the analysis for half wave, if you understand, full wave area you know, so the area is easy, right? Calculating the area is easy. So how to calculate the area under the parabola for 0 to t by 4? Yes, anyone? How can I linearize this piecewise? Because what is area under the square of the curve? If you want to calculate, you need to see the symmetric areas. This area is equal to this area. Agreed or not?
Yes, sir.
Then this area is also equal to this area. So if I know this equation and I try to integrate and determine the square of the area under the square of the curve for this part only, then I can calculate for other also by symmetry. So if this is 0 and this is A or this is V, I can write. What I can write? What is the slope? V minus 0 divided by T by 4 minus 0 is the slope. And since this is a 0, passing through 0, so the line equation will be V y of t is nothing but V by T by 4, which is the slope, times time. Agreed or not? For this part only, this interval only. Then let us find out the square of that. For y square of t, v square divided by t square by 4 square, which is 16. This is a constant. And then you have t square, right? So now for this curve, I can find the area for 0 to t by 4 interval. Up to this is clear?
Yes, sir.
I hope the screen is having some latency. Yes. So let us determine the area up to t by 4 for this curve. Area, okay. What area? This area, this cross marked area. So v square 16 v square by t square you take out, and this is t cube by 3, having the limit 0 to t by 4. So what you get? Correct?
Yes, sir.
So this is 4 and this is 12. So this one was the area of that one part. Now I am doing for half wave. So half wave means what? How much area will I get? 2 times of this. So I am writing here for half wave. What is the net area? 2 times v square t by 12.
Yes,
Now
sir.
mean of one time period is 2 times v square by 12, which is v square by 6.
6.
Now you need to root RMS.
V by root 3.
V by, is it root
Root
3?
6.
And for the other one, which is having a full wave, so this is for half wave. Now full wave let us do, okay? Full wave, how many times you would have this area? 1, 2,
4
3,
times,
4.
sir.
So 4 times v square t by 12, and then you mean over one time period, and then you root. So that will be the RMS strength. So v by root 3. And similarly for sine, if we do, I have shown you already. So I think we have completed all the three, right? For square and for sine, the half and full wave outputs and their RMS value and average value we have already calculated. Now we can go back to the problem. Up to this is clear to everyone? I want to hear from you. If you have any doubt, please ask.
Sir, RMS value of the sinusoidal wave. Please, sir, repeat.
RMS value. Okay. Yes.
Yes, sir.
So you see sine square theta d theta, but limits will be from 0 to pi, 1 by 2 pi whole root over for the half wave, and for the full wave 0 to 2 pi sine square theta d theta, but limits will be over 1 by 2 pi. Agreed?
Yes, sir.
So try to calculate.
Okay, sir.
In either case, this will be v square. So if you take out, it will be v times some factor. So what factor? It will be integral of sine square theta d theta from 0 to pi, 1 by 2 pi whole root over. So what is that factor? I want to hear.
So 1 by 2.
Correct. But it will not be 1 by 2 for both the cases. So for one, it will be 1 by 2, and for one, it will be 1 by root 2. So for the half wave, it will be 1 by 2, but for the full wave, it will be 1 by root 2. As you know,
Okay.
for AC signals, for full wave, because the RMS value is nothing but the square of that over the full scale, so 1 by root 2 only, right? But if its strength gets reduced by half, and then you have to square and then root, then 1 by root 2 another factor comes and it becomes 1 by 2. Because the area contribution by 2 lobes will double for full wave. But for half wave, area contribution will be half. And you have already taken a root, so 1 by root 2 factor will come. And when you multiply 1 by root 2 factor with full wave, you get the half wave. Hope you understand. So these are all RMS values. Any problem in this step?
No, sir.
Now you see, now you know all the signals and their RMS and average strengths. This much is clear. So you go back to the problem. What instrument were you having? You were having a PMMC type instrument. This is very important to note that PMMC type instrument can only measure the average value. So you need to know the average value of the signal. For example, square wave, triangular wave, and sinusoidal wave. Now see the first case. For example, we have a square wave. And for 10 volt of applied DC voltage, you have full scale deflection. But similarly, when you apply this 10 volt with AC, you have 40% deflection. So what you can conclude about the strength of the signal, about the peak strength of that AC signal?
So from the DC value, we can calculate the AC RMS value.
So for 10 volt DC, if I apply the square wave, so, and for obviously for this signal, what is the average value? If I half wave rectify it, because this signal is passing to the instrument like this. So signal is coming, and then you have the voltmeter connected like this. So the negative part of the signal will be eliminated. And what will be the output? Which the voltmeter can only sense like this, right? So T by 2 and T. So what is the average value of this signal? So meter reads only
A
this
by
one.
2.
Correct. And another information is given to you, which will help you to find the strength of this signal. What is this information? That
is 40% of deflection.
Correct. 40% of deflection. 40% of what deflection? Full scale deflection. So what is the full scale deflection?
A by 2.
No. That is one parameter, you know. But A by 2 is unknown, na? Another information. Another information is given to you. Please read this problem. That the full scale deflection occurs with 10 volt of DC. So if the average voltage strength is 10, then that is 100% of deflection of that scale. So 40% of that full scale deflection will give you the equivalent deflection for this applied signal. Agreed or not?
Yes, sir. A by 2 equals to.
Yes. See, this is FSD, full scale deflection. So 40% of this is nothing but A by 2.
Yes, sir.
Because
That is a 4D.
Information is given. That information is given to you. Okay. And you need to do this for 3 cases. One for square, one for triangular, and one for sine. So for first one, the half wave rectified version, you have already calculated that the average strength is A by 2, for which you can equate these two. And what is the A coming for first case?
Sir, 8 volt.
Yes, what is coming?
8.
Yes, 8 is coming, right? Now you do it, same thing. Yes, this is okay. So again, you pass the triangular wave. So this is the original signal. And then it went to a diode, a half wave arrangement. So what is the meter getting? Across meter we have what kind of signal? 0, T by 2, and then T. Okay. So this is the signal. Now what is the average value of this signal? How to calculate if this is the A?
So A by 4, sir.
Yes, half into height into base divided by whole time scale. Even if you forget, you can have the mean to calculate. So output signal, if I write as Y, then Y average can be calculated as A by 4. Now for this A by 4 in case 2, which is the triangular half wave rectified version, we have 40% deflection. 40% means 0.4 of the full scale deflection. If you want this, then what will be A?
Sir, 16 volt.
Yes. Now for case 3, if you give a sine and you have the original signal as sine and you pass it with the diode and the meter arrangement, then the meter will only read the half positive lobes for T by 2 period, and then it will read 0. So what is the average of this? I told you V peak by pi. Now V peak here is nothing but A. So it is A by pi. So A by pi is nothing but 40% of 10. Because it is a linear scale, you need to understand. 40% of full scale deflection means 40% of 10. We can do linear scale, okay? Because PMMC is linear. So what is A for this case, third case? Please note this is A. Yes. What is 4 pi? You need to give me the decimal value. Not 4 pi. Please check correctly.
Sir, 12.56.
Correct. Yes, now it is correct. Yes, it is 4 pi. Okay, correct. But in the exam, you need to give in decimals. Okay. So same, this was the arrangement. So hope you can do this problem. Same problem is there and it is asking you. Just read this problem. This problem is a full bridge kind of arrangement. Hope you know what is full bridge. It allows both the positive and negative half and brings it to the top positive cycle, positive half cycle. Okay. There is a rectified one. So here you get the DC. DC means I am meaning the average value of the signal. So PMMC will read the average value. So try to do this problem. So assume that current coming to this network is sinusoidal. Okay, IAB. And if you have a sinusoidal current and passing through a bridge, then what will be the shape of the waveform? For example, I assume that IAB is sinusoidal, right? So this is 0, this is T by 2, and this is T. And this is, for example, Y of T. Then after I rectify it using a full bridge, then your Y dash or Y double dash I can write for full bridge. How will it look? So this is the input node and this is the output node. So this is the output node. So at the output node, which is Y double prime of T, and this Y of T is the input. So what is the 0 to T by 2 I told you, right? So what is the average value?
Sir, V by pi. That is the I by pi.
Correct. But for half wave, it was I by pi. For full wave,
yes,
it will
2
be
I by pi.
Yes. Because for half wave, it was not having strength in or contribution for the other half. But here you have contribution. So 2 times it will come. 2 times I peak by pi. This is the average value. But PMMC meter, you know, is reading 2. So 2 times I peak by pi, which is the average value, is nothing but 2. Agreed or not?
Yes, sir.
Now using this equation, since I peak was not given to you, you have this equation. But what is asked in the question? The RMS value. So you need to be thorough with the RMS value of the output signal. What is the output signal? This one. It is a mode of sine. So you have the positive lobes. And what is the RMS value of that? Either mode of sine or sine of t, RMS value. Both will be same, right? So what is it? It will be peak by root 2. So RMS of output full bridge rectified signal. So either you rectify full bridge and then take the RMS, or you take the RMS of the sine signal. Both will be same. Agreed or not?
Yes.
Because you are squaring the signal and then doing the full mean of the time period and then taking the root. So both will be same. So RMS of output of full bridge arrangement, what it is? I peak by root 2. So what is I peak by root 2? Calculate. I peak is pi. This pi by root 2. consider the diodes to be ideal. I hope this is clear, right?
Yes, sir.
So now let us go to the final part of the session with this final problem. Try this problem. Try for 2 to 3 minutes and then I will give you some solutions. But first, understand what is given and what is asked out of the problem. So read the problem. So Rx is a variable resistance, right? Where it is varying from 0 to 1 kilo ohm and you have the varying deflection scales. And the meter is a PMMC meter, okay?
Yes, sir.
So what you want to achieve is that you want to achieve a half scale deflection when you put the value of Rx to be 1 kilo ohm. So accordingly, you need to design the value of R1 and R2. Because if you don't design R1 and R2, then it will violate the current carrying ability of the instrument or the current rating of the PMMs that you have to obey. The full scale deflection current 1 milliampere, you always need to obey. So for no condition, it should go out of that bound. And accordingly, you need to design the value of R1 and R2. Rx is a variable resistance, okay? And the question asks that if you have 1 kilo ohm as Rx, you want to get the full half scale deflection. What is the meaning of half scale deflection? Can anyone tell me? PMMC is a linear device. So full scale deflection, if it is happens at 1 milliampere, then half scale deflection will happen at yes. How much current should it flow to the meter so that you can get half scale deflection? It is a linear meter, right? So how much current should flow through the meter such that you can get half scale deflection? If the full scale deflection is 1 milliampere, how much current should flow?
So 0.5.
Correct. 0.5 milliampere, right? So 0.5 milliampere, it will give half scale deflection.
Yes, sir.
Now that much you know, but it should give 0.5 milliampere only when this resistance is 1000 ohm. So that is one equation. So how can you model that equation? If this is 10 volts, so 10 divided by Rx plus R1 plus R2 parallel Rn. This is the current flowing into this branch. Times if you have the other branch resistance divided by R2 plus Rm, right? This step is clear or not?
Yes,
This should be equal to 0.5 into 10 to the power minus 3, 0.5 milliampere. And here Rx is 1000. So for Rx is 1000, you are getting the half scale deflection. So 10 by total circuit resistance, and then you get the current, and that times the other branch resistance to get this branch resistance, this branch current as the half scale deflection current. And Rm value is given to be 90 ohms. R2 value you don't know, R1 value you don't know, but Rm value you know as 90 ohms. So this is one equation where you have two variables, R1 and R2, because Rm is known. But one more information you have, that it gives full scale deflection when Rx is 0. So full scale deflection means 1 milliampere. And then for that case, again 10 by Rx is 0. So I will not take into account the Rx. And R2 parallel Rm times R2 by R2 plus Rm. This is the second equation, where you have the full scale deflection current flowing into the meter for the overall arrangement. When you find the current through this part. Now using these two equations, try to find out the value of R1 and R2. You have only two variables. All variables are given. That is Rm is 90 ohms. And what else you need? Rx is given. Okay, 1000. Rx here is 0. You don't need Rx. So use these two equations. This is the first one. And this is the second equation, and try to determine the value of R1 and R2. So that you actually get the half scale deflection at 1 kilo ohm Rx. So try to determine. See, we can also simplify this equation. Okay. How to simplify? You have 0.5 milliampere current passing through this, right? So what is the voltage drop across this R1, R2?
So 0.5 into 90, 0.5
Correct.
milliampere.
Into 90, right? Divided, if you know this voltage drop, you also know the current, right? So this is this current. Voltage drop by resistance is current, right? Plus the full scale or the half scale deflection current. That is this one, is this current. So instead of writing this one, which one? This one, right? You can simplify as this one. So instead of applying the current division, you can just apply directly the current, because this current you can calculate. This current I am talking about. This current you can calculate as a sum of these two currents with a single variable R2. And effectively you can write this as 0.5 into 10 to the power minus 3 into 90 divided by R2, which is the voltage drop by R2 for this branch, plus this branch is having 0.5 into 10 to the power minus 3. Sum of this branch will give you this current, and this current is nothing but 10 divided by net resistance. Net resistance means 1000 for Rx plus R1 plus R2 parallel Rm. Rm is given as 90. So this will become much easier for you to solve. This is one equation, and second equation similarly you can write. Second equation how you can write? This is 1 milliampere. So 1 into 10 to the power minus 3, this much current if flows through 90 ohm, then that is the voltage drop in that case across R2. Divided by R2, you will find the current plus the full scale deflection current, which will give you this net current. And this net current in that condition will be equal to 10 divided by Rx. Rx is 0 in that condition. So 0 plus R1 plus R2 parallel Rm. Rm is 90, same for both cases. This is Rm. Okay. So these two equations are much easier to solve than these two equations. So you can just avoid and you can use these two equations because it will be easier to solve for you. Both will give you same result only, but these are easier to solve. 1 and 2. So you solve 1 and 2 and tell me how much you are getting R1 and R2. Yes. Am I audible? Hello?
Yes, sir.
Hello? Yes. Yes, you calculate how much is the value R1 and R2 using these two equations, where Rm value is known, right? It is 90. Please note. So using these two equations, you can just solve for R1 and R2. Only variable, two variables are there, and then Rm is the external resistance, which, Rm is the meter resistance, which is 90 ohm. And Rx is, I have already given you 1000 for one case and 0 for another case. So the meter resistance 90 ohm, you can just put it for both the cases and determine R1 and R2. So just try this. You can simplify, right? These values you can simplify. And try to find an expression for R1 and R2. Two equations you will get, then eliminate one parameter and try to determine R1 and R2. Do this exercise because it will be useful for you. Try to eliminate one variable at a time and then try to eliminate the one variable and then determine the final another variable. So what is the value of R1 and R2 you calculate? So you try it. R1 you will get, I am telling you the values, as 991 ohm, and R2 you will get as 10. So do this as a homework and just see whether you find these values. This exercise is important, so you can try. So R1 value you will get at 991 and R2 value you will get at 10. Okay. So try this as a homework. So any doubt? Hello?
No, sir.
Yes. So if you have any other doubt, you can just ask from the weekly lectures or some other doubts while solving the problem. Or if you have no doubt, we can just end the session. Okay. And we'll meet at next session. So
Okay,
try
sir.
this problem as a homework. Okay.
Okay, sir.
And try to solve these simultaneous equations. You will get the value. So if you have no doubt, I can end the session, right?
Yes, sir. Thank you,
Okay.
sir.
Thank you.